Alright everyone, it's Mr. Eddy back with yet another video. Today guys, we're going to begin our 7th unit in AP Chemistry, which is on equilibrium. I want to briefly start with a topic 0, which is on reversible processes, to serve as a preview to equilibrium. Okay, so without further ado, the term reversible as applied to a reaction is the ability to proceed in both a forward and reverse direction. So a reversible process then is a process that reverses direction by an infinitesimally small change, such as a temperature change or a pressure change, from the surroundings applied upon the system. Said change will cause the system and surroundings to return to its original state, and then there will be no net changes to the universe. A reversible process can be both physical and chemical. So if we take a look at a model here, the Carnot cycle, this illustrates a reversible process quite well. Now, I'm going to be upfront with you guys. There's a bit more thermodynamically occurring here in this model that I'm not going to explain today. Instead, I'm going to save that for Unit 9. I just want to show you what a reversible process would look like. Okay, so essentially, guys, what we have going on here is we have this container with a piston, and then the yellow substance would be a gas. And as you guys can see in images A to B, what's happening is that the gas is undergoing an expansion, and that expansion is driving the piston upward. When that happens, there is a point in which the piston and the gas will catch itself, okay, and begin to compress. As the gas begins to compress, the piston is driven back down to its original position in the container. That is a reversible process. This piston and gas being able to again go through an expansion in which the gas drives the piston upward, and at a certain point the piston will stop and the gas will undergo a compression, and that will have the piston will be driven downward until it reaches its original position. That is a reversible process. We're going to talk about why that occurs, what's actually happening thermodynamically to cause this reversible process in Unit 9, but nonetheless, I wanted to show you what it would look like. And again, it's this idea that both the system, which would be the piston and the gas, can return to its original position if acted upon by some force in the surroundings. Okay, so that is a reversible process. Now the question is, are all processes reversible? And the answer is, of course not. Okay, there are irreversible processes, which is a process that cannot be reversed, meaning the system and the surroundings cannot return to its original state. Now, guys, in your first year of chemistry and in most of AP Chemistry thus far, you know, I may have hinted to you that there could be such ideas that are reversible, but for a large portion of your time at school and your chemistry classes we've really been focused about irreversible processes, right? Things that occur in one direction, and so on and so forth. Now, examples, of course, would be cooking an egg, okay? Burning wood, rusting metal, digesting food, heat transfer. Again, these are all things that are irreversible, meaning once you do it, you can't undo it, okay? So when we get into looking at, for example, cooking that egg, right? An egg would begin water soluble, but as you heat the egg, you are denaturing it, and you remember, egg is essentially just a protein. So as you denature the protein, what ends up happening is you cause new bonds to form, and that is called disulfide bonds. And it turns out that breaking these disulfide bonds when the egg is cooked is extremely hard to do. So it's extraordinarily almost impossible and unlikely to reverse this. Okay, so, and then of course the property of the egg protein, the albumin, changed, right? It started off as water soluble and then it became insoluble. Okay, burning wood is another one, right? After you burn wood, you can't take the ash and reform the wood and also recapture all the energy that was released in the form of the fire and the light. Just can't happen. Rusting metal. Although you can use metal wool to polish metal, right, and essentially just eliminate the rust. That's all you're doing though, is when you're eliminating the rust is falling and the rust is now separate from the metal, but you still had the rust occur. You can't unrust something, okay? Digesting food would be another case, right? You're taking very, very large molecules and you're breaking them into smaller and smaller and smaller ones. And, you're doing, and each time you do that, your body is taking the energy that was stored in the food and it's converting it into chemical energy. You can't undo that. Once you start digesting food, it's going. You're breaking you're breaking very big things up into small things. And then, of course, as we learned about in Unit 6, heat transfer. Heat will transfer from a hot substance to a cold substance. Once it does that, it can't untransfer, right? That's not how things work. Again, some more things at play here of why that occurs specifically is a thermodynamic quantity that we're going to talk about more in Unit 9 called entropy. But nonetheless, I wanted to mention it here. Okay. So, revisiting our reversible processes then, well, what are physical reversible processes? So we did talk about this before, right? We've talked about phase changes, right? Freezing, melting, vaporization, condensation, sublimation, deposition. All of these phase changes are indeed reversible, right? I can remove energy as much as I can put energy into the system, and this can cause water to melt or water to freeze, water to boil, water to recondense, and so on and so forth. Okay. Dissolving and crystallization, straightening and curling hair. This is very interesting in terms of biochemistry, guys. The heat will break hydrogen bonds in your hair. So if you have curly hair and you were to go to straighten it, what you're breaking is the hydrogen bonds. So since that's an intermolecular force only, those hydrogen bonds can reform after a time and, your curly hair come back. Okay. Same would the vice versa is also true. If you have straight hair but you use a curling iron, what will end up happening is the hydrogen bonds will reform themselves and then you'll reform your straight hair after a time. That it would be a physical process there. Expansion and compression of springs. And then, of course, here's a model showing our phase changes, right, where we're going through various different ones, showing that, yes, they are indeed all reversible, depending on when you're putting energy into the system or if you were releasing it to the surroundings. And then, of course, here's a picture of sugar recrystallizing. One of the things I like to think about with this one, guys, is, if you, in the summertime, if you get iced tea, you get iced coffee, right? If you put too much sugar in it, what ends up happening is that the sugar will end up crystallizing in the container. We talked about that in Unit 3, that the reason why that does that is because solubility, right, the ability to dissolve something into a liquid, is dependent upon temperature for solids. So the colder you are, the more likely you can recrystallize something, right? Well, that's reversible. So I can equally dissolve something and I can equally recrystallize it, right? If I have salt water, I could separate the two things by distillation, right? Meaning that I can boil off the water. The water is collected through the condensation, a portion of the distillation apparatus, and then the salt would be collected in the vessel in which we went undergo boiling. But in the same instance, so that recrystallized the salt, but I could easily redissolve it again and just add the water back, and I have salt water again. So again, all these things would be reversible. Now, some chemical reversible processes would include redox reactions, right? The transfer of electrons. So, and when I say redox reactions, guys, obviously the caveat's not all redox reactions do this. Obviously, an example of a redox reaction that is irreversible would be rusting. However, there are some redox reactions in which we can transfer the electrons again, and that would be like a rechargeable battery. So if you're taking a look here in this model here, as the battery is being used up, the electrons are flowing from the anode to the cathode, and I can reverse this by charging my battery, and then those electrons are going to flow back from the cathode into the anode, and I get to reuse those electrons again. That is an example of a reversible redox reaction, a rechargeable battery. We can also reverse acid and base reactions, which would be specifically the transfers of protons. We're going to talk about more about this one in Unit 8, so more on that next unit. And then, of course, we can look at some gaseous reactions here. A very common one is hydrogen gas reacting with iodine gas to form hydrogen iodide, okay? As a gas, though, these HI molecules, hydrogen iodide, can react together and reform hydrogen gas and iodine gas. So that's a reversible chemical reaction. Now, guys, that's not to say that you can't have reactions in which you have, for example, when ammonium chloride is heated, okay, it will form ammonia gas and HCl. And as that reacts in the air, if you take it off the heat, that can reform ammonium chloride. Okay, so it's not always a gaseous reaction. There are other examples of reversible processes that I don't have on the slide, but these are the big ones that I wanted to mention today. Now, in terms of factors governing a chemical reaction, we're going to start to see AP chemistry start coming together big now. Okay, so we're going to see that, for a little bit we were just, it felt like we had to get through a lot of foundation work before I could start pulling things together. Starting in Unit 7, I'm going to be pulling a lot of things together now. So as you are all aware, in Unit 5, we saw that a speed, or the rate of a chemical reaction, was determined by the kinetics. And we know the kinetics had a host of things, but really, if we dived into it, if we were thinking about collision theory, we talked about a multitude of ways in which we could increase the rate of a reaction, right? So increase its speed. Okay, that was all in Unit 5. And then in Unit 6, we were introduced to something called enthalpy, right? Which we really talked about it as essentially heat energy moving in or out of the system, right? Now, enthalpy is part of a bigger thing called thermodynamics. And what thermodynamics determines is the extent of a chemical reaction. And guys, we're going to talk about this extent of a chemical reaction. We're going to talk about a small piece of it in Unit 7, which is obviously equilibrium. So specifically in this unit, guys, we're going to describe how far a chemical reaction is going to go based on an experimentally measurable quantity called the equilibrium constant. And a large equilibrium constant basically tells us that the reaction is going to go to nearly completion, which means to us it favors the products. A small equilibrium constant will indicate that the reaction barely proceeds at all, which means to us the reactants are favored. With that said, that is our preview of Unit 7. I will see you on the next video. Have a good one.